Hey, we're very happy to have Yue Zhao, who's come from the greatest snow on Earth, to tell us about searching for dark photon, dark matter with gravitational wave detectors.
All right. Thanks a lot for the invitation, and it's really nice to be here. And I think this has already been my third or fourth trip to UC Davis. I really like this place. And so today I'm going to talk about how to use the gravitational wave detector, such like LISA or LIGO, to look for the dark photon, dark matter. So basically, the idea is to steal this gravitational wave detector, and the performance study has nothing to do with gravitational wave, but use it as a dark matter direct detector. Okay, so today's talk will be based on the theory paper that I worked with Aaron Pierce, who is a theorist at University of Michigan, and Keith Rouse, who is an experimentalist from University of Michigan and a senior member of LIGO collaboration. And this is the theory paper that we lay out the idea and draw the curves. And there are some ongoing data analysis that is we are pushing for using the publicly available run-one data of LIGO. And within this talk, I'm going to present you some very preliminary results on using the O1 means operation 1, LIGO's O1 data to look for the dark photon dark matter. And the interesting thing here is actually only using the O1 data, we have already been able to carve into the unexplored parameter space already. So even with the short runtime and a little bit poor quality of the data, we have already done a better job compared in a small mass window, already done a better job compared to other experiments. And you can imagine that for a full run of the 04 and 05 of LIGO, then we can carve into a large parameter space. So this work has already been internally reviewed by LIGO, and the data analysis O1 is almost done, and we are actually polishing our paper. Hopefully we can make sure the first 3 digits are correct for this prediction. Okay, so let's just start with a very quick review about the current status of particle physics. So we have already seen this particle table. We have already known this particle table for a long time, and then back in 2012 we find the Higgs boson. And at the end of 2015, the LIGO gravitational wave detector made a first direct measurement of the propagating gravitational wave, which made a huge wave. And then the natural question here is that whether we can find a nice bridge between the particle physics over here and the gravitational wave astronomy, and whether it's for a particle physics person, I'm most interested in the fact to ask the question on whether we can use the gravitational wave detector to make any measurement of or probe the new physics beyond stand model. So I don't think I need to waste a lot of words on why we need to look for dark matter. There are many independent and solid evidence to show that dark matter really exists, and we really have to look for it. So the dark matter makes up about 26% of the energy density in our current universe, and that is a huge amount of energy, but we have basically no idea about its property. There are several things that we roughly have the idea from the numerical simulation. For example, we know that the local dark matter energy density is about 0.4 GeV per cubic centimeter, and if the dark matter is like a WIMP particle whose mass is about 100 GeV or TeV, roughly speaking, within one coffee mug there is one dark matter particle. And also we know that the dark matter velocity roughly speaking, follow the Maxwell-Boltzmann distribution. So its typical velocity is about 10 to the negative 3 speed of light. And at last, dark matter cannot be very hot, so that basically rules out the possibility for stand model neutrino to play the role of the dark matter. However, there are many things that, yes?
I think only a fraction of dark matter can be hot.
Yes, that's right. So 10%, I think that's the upper limit. So there are still many properties of the dark matter remains to be unknown, and especially for the mass of the dark matter particle, there is a huge theoretical uncertainty. So the lightest choice can be as small as 10 to the minus 22 eV, whose de Broglie wavelength in the dwarf galaxy is comparable to its core size. And in the heavy regime, the dark matter may not be even a particle. It can be composite object, such like primordial black holes, and its mass can be about order of the solar mass. So there is, roughly speaking, a theoretical uncertainty for the dark matter mass at order of 100, order of magnitude uncertainty. So in this talk, I'm mainly focusing on the ultralight dark matter regime, whose mass range from 10 to the minus 22 eV to about 10 to the minus 2 eV. So within this regime, you'll get a large occupation number for the dark matter particle according to the known dark matter energy density. And there are several good choices for the dark matter particles. One is the axion, whose mass is protected by the shift symmetry. The other is the dark photon, which is the key focus of today's talk. And the dark photon's mass is protected by the gauge symmetry. And so those are this is the ultralight mass regime. And for the ultra heavy mass regime, we have the primordial black hole can play at least partially the role of dark matter. And the cool thing is actually we realized that using the Gravitational wave detector, one is capable to probe both the ultralight mass regime for dark matter and the ultra heavy dark matter mass regime. If I have time, I can very quickly comment on how to use laser-like Gravitational wave detector to look for the primordial black holes. Okay, let's just focus on the ultralight mass regime. And the dark photon that is the particle that we're going to study. And the dark photon that we consider in our paper we assume is the gauge boson of the U1 baryon gauge group or the U1 B-mass cell gauge group. And the U1B gauge group, we know the baryon number is not anomalous in some model, but here I basically just ignore this subtlety because one can imagine the U1B can be cancelled out by adding in new particles or using the very advanced mechanism such like the Green-Schwarz anomaly cancellation mechanism. So from now on, I'm not going to worry about the anomaly for the U1B and treat it at the equal footing at the U1B myself. So as I mentioned previously, that in the ultralight mass regime, the occupation number is very high. And in that case, it's more proper or it's easier to treat the diameter as an oscillating background field instead of each individual particle. And for the dark photon, it's basically you can think about this as an oscillating background dark electric field. I'm going to give you some details later. And the idea is very simple. It's basically saying that if I have any particle that carry the charge of U1B or U1B mass cell, it will feel the existence of the dark photon dark matter background and then being oscillated by the existence of the dark matter. I'll give you details later. Okay, so let me firstly comment on how to make the dark photon to be a good candidate of dark matter. So first of all, it has to be massive because it cannot be relativistic. So it can get its mass through the Higgs mechanism, or because we are considering the case where dark photon is the gauge boson of a U1 abelian gauge group. So we can actually directly use the Tuchelberg mechanism, which is a very special mechanism for the U1 abelian gauge group. And you can think about the Tuchelberg as a special limit of the Higgs mechanism. And also, the dark photon can also have again the correct dark matter radical abundance. It cannot be thermally produced because it's very light, but there are many different choices for the non-thermal production mechanism. For example, the misalignment mechanism that was discussed by many groups already, and there are recently some studies on producing the dark photon dark matter through the light scalar decay, either through the parametric resonance production or the tachyonic instability. And then last, there is a paper by Lin-Tao Wang and Andrew Long that is talking about the dark photon production from the cosmic stream. So there are all kinds of choices for the non-thermal production of the dark photon to play the role of dark matter. So let's not worry about that. So all in all, this slide just want to make the claim that the ultralight dark photon can be a good candidate for dark matter. Okay, so that's everything about the dark matter side, and let's get into some details about the gravitational wave side. So for the gravitational wave detector, the most popular choices are the laser interferometers. And there are two categories of the gravitational wave detectors. One is the LIGO-like gravitational wave detector, which is ground-based. So this is the picture of one of the LIGO gravitational wave detector. And this is one arm of the gravitational wave detector, which is about 4 kilometers long. And for LIGO, it has already achieved amazing sensitivity for the displacement of those mirrors. They can actually achieve the sensitivity as good as 10⁻³ of a radius of a single proton. So this is such an amazing sensitivity, and the detection of the gravitational wave got them the Nobel Prize in 2017. And this is a fascinating point because it opened a new field, which is the gravitational wave astronomy. And as a particle physicist, my most interest lies on the building the bridge between the gravitational wave astronomy with the particle physics. The second category of the gravitational wave detector is a space-based gravitational wave detector, such like LISA. So the plan is quite significant. So they want to shoot 3 satellites forming a equal edged triangle, and then the central mass will rotate with the Earth on the Earth orbit around the Sun. Okay, the arm length here is 2.5 million kilometers, and for the LIGO it is about 4 kilometers. So there is a significant difference. And the LISA has already been going on for like many decades, and recently the LISA mission is finally approved by the European Space Agency, and NASA decided to rejoin the program. And the LISA Pathfinder, which has already demonstrated that the noise they want to achieve is really achievable. So it's a big success. So now let's talk about how to use the gravitational wave detector to look for the dark photon dark matter. But before that, I want to briefly review how the gravitational wave detector is supposed to be used to look for a gravitational wave. So for the laser interferometer gravitational wave detector, it's basically just a very advanced Michelson-Morley interferometer. So we have the laser emitter from here, and then here this thing is the beam splitter. You shoot the laser to the beam splitter, you split the photon into this arm and this arm. And along each arm there are 2 mirrors, and the photon will bounce back and forth between those mirrors. And the quality factor is about 300. So after the photon comes back from the trip, it will re-meet at the point and then generate an interferometer pattern at the photon detector. And when you have the gravitational wave pass by, what it will do is will modify the metric between those 2 mirrors. And remember, those 2 mirrors are separated from each other about 4 kilometers for the LIGO. So when the gravitational wave comes by, it will modify the metric over within this region, and that will affect the photon's phase when it comes back to the photon detector. And that's how you make this detector work. So it's basically a precise measurement on the relative change of the arm length between those 2. And now let's look at how the dark photon dark matter will do for this gravitational wave detector. So as I mentioned previously, that the ultralight dark matter is you should think about this as a coherently oscillating background field. And just like what happens if you put an electron in the radio wave background, the electron will respond to the electric field of the radio wave and then start to oscillate. The same thing will happen to the test object, like a mirror on the gravitational wave detector. It's because the mirror carries a huge number of baryon, carry a huge baryon number or Bman number. So it carries a huge charge, and it will feel the existence of the dark photon dark matter field. So this mirror will start oscillate, and this mirror will also start oscillation. And however, this mirror is well separated from this mirror in the spatial position. So although they are both oscillating under the same dark photon dark matter field, but they are sort of out of phase. And once they are out of phase, you can actually literally changing the distance from this mirror to the other. And the same happens on this arm. So that is why the dark photon dark matter will introduce a relative change for the arm length. And that's how we make the measurement of the existence of dark photon dark matter. Okay, so this is just a very simple physics observation, and that's the physics behind this proposal. Okay, so in order to estimate the sensitivity, we have to firstly calculate what is the maximum displacement one can achieve using this detector. So the first thing we want to calculate what is the magnitude of the dark electric field. So as I mentioned previously, the local dark matter energy density is about 0.4 GeV per cubic centimeter, and because all my energy is approximately all deposited into the potential energy, so I can use this simple equation to estimate the size of the gauge potential. And this is just, and then after you get the magnitude of the gauge potential, you can do exactly the same thing at the U1 ENM or U1 ENM and define the dark electric field and dark magnetic field. And of course, because this is a massive photon, and in order to eliminate the superparticle inside of the stored in the Lamchiel mode, let's choose the Lorentz gauge fixing condition. And with this condition being fixed, one can directly go ahead and calculate the dark electric field and magnetic field. The dark electric field is because it's proportional to NA, because it has the time component differentiation acting on the gauge potential. That's why it brings down a power of NA, because mostly the energy is coming from the mass energy. And for the magnetic field, because everything is spatial derivative, so you are supposed to bring down the momentum of the field, and that's why it has an additional power of V. So as we know that V is a number which is about 10 to the minus 3, so the magnetic field, the dark magnetic field is much, much smaller compared to the dark electric field. And that's why we only, in the later discussion, only focus on the dark electric field, because the magnetic field is not that important. Okay, so after we get the estimation for the dark electric field, now we are ready to calculate the acceleration, which is a trivial step to move forward. And this dTA vector, it is the approximation formula to calculate the dark electric field. And the second piece in this equation is the charge mass ratio. And if we are talking about a silicon mirror, which is currently the mirror that is being used at LIGO wave detector, if we choose the gauge boson to be U1 barium, to be U1B gauge boson, then the charge mass ratio is 1 per GeV, because the huge Avogadro constant got cancelled, both upstairs and downstairs. And if we choose the dark photon to be the gauge boson of U1B mass L, then the charge mass ratio is 1 per 2 GeV. Okay, so there is just a trivial factor of 2 difference. Because for the silicon mirror, the barium number from proton got cancelled by the lepton number for the electron, because you assume everything is charge neutral. So the only contribution to the U1B mass L is coming from the neutron. And if time allows, I can also very quickly comment on how to use this exactly the same proposal to look for the kinetically mixed dark photon instead of just the U1B and U1B mass L. But let's wait to the end. And now, after you get the formula for or the equation for the acceleration, then use to do the physics 101, you do the 2 time integral for twice, and you get the displacement. And because for the laser interferometer, it only measures the displacement along the arm, so we have to do the projection along the arm here. Okay. Yes.
I'm sorry, I'm a little confused here. For that calculation looks as if you're assuming that the acceleration of the two mirrors at the opposite ends of the arm is opposite.
Good.
They're shifting in the same direction.
Absolutely. So that's an excellent question. I'll show you in this slide.
Okay.
So this is just calculating the displacement for each mirror.
Okay.
And then the crucial thing is actually to calculate the relative change of the arm length.
Okay.
So here I'm only preparing the calculation for this one, for each the mirror, and then the crucial thing here is to, after you calculate the displacement as a function of time along the x-axis and the y-axis, you have to subtract all of them in order to calculate the change of the photon phase.
Okay.
Okay.
And the other question
Yes.
I have is, what determines the direction of this?
Oh, very good, very good. Can I leave this question for later discussion? Yeah. So a very quick answer for that is that within the so-called coherent region, I'll define that later. The propagation direction and the polarization directions are two totally random vectors, but fixed vectors. And then if you say that I do the measurement within this short period of time, I will have a random direction for my signal. But if I wait for another period of time, then this direction will change to another, the force will change to another direction. But I'm going to show you that right now. Okay, so this is the detector configuration for LIGO, and it has the open angle of 90 degrees. And this is a very simple picture for LISA, and it has the open angle about 60 degrees. So for LISA, there are actually 3 pairs of the laser interferometer. And later I'm going to tell you some subtleties, like, for example, the pair 1, which is coming from ZX and XY, they share the same arm as the XY for the pair 2. So there are some subtleties on how to make the correct linear combination of the 3 detectors signal in order to get in order to make sure the background is totally independent of each other. But I'm going to tell you about that later. And the key thing here is that I want to calculate the relative change of the arm length in order to extract the sensitivity of the dark photon dark matter.
Question.
Yes.
For each mirror, you're assuming that it's oscillating along the direction of the arm.
Yes.
But wouldn't as well oscillate in the direction of the
It will. It will. So there.
Is it negligible?
That's not observable, because oscillating along this direction, for example, for this mirror, it can go this way. This will change the arm length. That will change the length of the photon's propagation. But this moving up and down doesn't work. Okay. And the key thing here is we are going to calculate the relative change of the arm length, and eventually compare this with the sensitivity of the Gravitational wave detector in terms of the Gravitational wave string. And then that's how we are going to proceed the calculation and eventually extract the sensitivity. And as I mentioned previously, that the key thing here is to measure the relative displacement, not the displacement for each mirror. That's why here, as you can see, my relative change of the arm length is proportional to k, which is the momentum of the dark photon dark matter. So if the momentum of the dark matter is 0, then my dark photon field is just a universal field everywhere. So my mirror, those mirrors will experience exactly the same force at the same phase, and that won't cause any observable effect. That's why this k here is the crucial component, and of course we suffer from a 1 power of suppression coming from the vertical velocity. Okay, and the other thing I want to mention is this triangle bracket stands for the averaging on all the directions. And the thing that I just have already commented on is that for a non-relativistic particle, the propagation direction and the polarization direction, they are totally independent to each other. So when we do this average, we have to do 2 averages for the 2 random directions. Okay. So we can very quickly comment on compare our proposed search with very famous other dark photon dark matter or axion dark matter experiments. One of the famous one is the ADMX, which is operating at Washington, Seattle. And for ADMX, you are converting the dark photon or the axion into this resonant cavity. But in this case, in order to search for the dark photon or axion, you have to fine-tune the resonant frequency of the cavity every time you do a measurement, and then that will. So hopefully, each time when you do the tuning, you can accidentally match the frequency, the resonance frequency, with the oscillating frequency of the background field. But for the LIGO Gravitational wave detector, since we are not relying on the resonance effect at all, so we are doing a whole frequency band search simultaneously. We don't have to scan the frequency as what ADMX is doing. Okay, now let's talk about some spectacular features of our signal. So first of all, because dark matter is non-relativistic, so its energy is dominantly characterized by its mass. So our signal is mainly oscillating at the frequency determined by the mass. So our signal is really, really fantastic because it is sort of monochromatic. It's precisely the same as the signal when you have have a monochromatic gravitational wave passing by. And what you should do in order to search for such kind of signal is that when you do the measurement as a function of time, then you do the Fourier transform and look everything in terms of in the frequency space. And if there is a signal, then there should be a bump. One should perform a bump counting experiment in the frequency space. And having a single bump in the frequency space is not the end of the story, because there are even more striking and interesting features showing up in our signal. So our dark matter is not precisely at rest. It has a velocity distribution controlled by Boltzmann-Maxwell distribution. So there is an intrinsic broadening of our signal. The intrinsic broadening of the signal is about 10 to the minus 6 times the central value of my signal frequency. So for example, for LIGO, if we are talking about a frequency, a signal showing up at 100 Hertz, then the broadening is about 10 to the minus 4 Hertz. And the cool thing is actually for LIGO, the operation time is long enough, so the frequency resolution is fantastic. It is much better than 10 to the minus 4 Hertz. So in that case, you can actually get into the details for the bump, and then extract all the information within the bump. And later, I'm going to show you some detailed study about the power spectrum after you do the Fourier transform. And you'll see some very cool features about this signal. So the key thing is that if once the dark photon dark matter is measured in this way, we can actually extract a lot of detailed information for the dark matter. And the other thing that I want to emphasize is that there is a quantity called coherent distance or coherent region. And the physical meaning for the coherent region, it means that within this region, I can approximately treat my dark photon dark matter as a plane wave. And my deviation from the plane wave starts to be order 1 after I wait for a long time, or I go for a distance which is very long. So let's just calculate. Let's just look at the length of the coherent region for the signal showing up at about 100 Hertz. So if you choose 100 Hertz as your signal, then the coherent length is about 10 to the 9 meters, which is way longer compared to the size of the Earth. And within this region, I can approximately treat my dark photon dark matter as a plane wave. And this is really great, because that means everything on the Earth will experience exactly the same dark photon dark matter background simultaneously. So we are going to use that fantastic property and help us to build up our signal noise ratio. And here is the picture. So for LIGO, there are actually 2 detectors. One is at Hanford in Washington, the other at Livingston in Louisiana. And the separation between those 2 detectors is about 3,000 kilometers. And this curve represents the dark photon dark matter profile at certain frequency. And as you can see, this profile is actually expanding much longer distance compared to the separation of those two detectors. So those 2 detectors will experience almost the same signal as at the same time. And then we can actually correlate the signal received over here and the signal received here in order to further beat down the background and perform a correlated search. And this is a crucial point, and then I'm going to tell you how to include the correlation in the later calculation. Okay, so that's everything about the some physics pictures, and now let me get into some detailed calculations. Yes.
Just one more very naive question. Why is this field a plane wave rather than standing wave?
Very good.
Because if it's a standing wave, you won't get any signal, right? Because both then.
I maybe got a little bit confused. What do you mean by standing wave? Standing wave, you have to have the node, and by imposing the boundary condition, that's the standing wave. But even a standing wave, I can still have the signal as long as I have a spatial profile.
Well, but if your spatial profile is much larger than the distance between Washington and Louisiana, then it's certainly much larger than the distance between the mirrors.
Oh, I see your point, yeah.
The question is why
good.
why the two mirrors, which are a distance that's much shorter than this
Yes.
coherence, that
Yes.
still have different
Very
accelerations.
good, very good. Yeah, so this is precisely the competition between the difference in two mirrors versus the difference of two detectors. And it turns out that, so you gain definitely, so let's say that I have the freedom to tune my dark photon's velocity. If I tune it to be very large, then I start to gain stronger and stronger signal in my detector, but I will lose the coherence between this detector versus the other. But if I make the velocity to be small enough, then I have the correlated signal everywhere, but each signal becomes quite small. So there is actually a competition, and we include both effects in our calculation, and it turns out that those two compete with each other, but still give us an observable effect.
Okay.
Okay. Okay, so now our task is to estimate carefully the sensitivity of the LIGO or LISA vertical wave detector with respect to the parameters of the dark photon dark matter. So the trick that we are going to play with is to firstly calculate the gravitational wave sensitivity in terms of the gravitational wave string. As I mentioned previously, the signal is almost very similar to a monochromatic gravitational wave passing by. So we can just study what is the sensitivity of a monochromatic gravitational wave in terms of the gravitational wave string, and then translate that in terms of the dark photon coupling constant and oscillation frequency. So for a gravitational wave signal, it is theoretically characterized by one-sided power spectral function, and it is proportional to this omega GW. Omega GW is just the differential energy distribution, and is defined in the following terms. So the crucial thing here is that the one-sided spectral function is proportional to the energy density distribution, differential distribution. And because we are dealing with almost a delta function in our spectrum, so the differential distribution is quite easy to be calculated. And so, however, as I mentioned, that the frequency resolution of LIGO is good enough to resolve the finite broadening of my signal. So one can actually, the shape of the signal is concretely predicted by Maxwell-Boltzmann distribution. So in principle, one can go beyond a simple bump counting experiment in the frequency space, but do a more complicated template search. And we are actually in the progress on doing this part of the search. I'm going to show you some results, some surprising results that we got for the template, and you'll see that there is no way that the background is capable to fake the signal. And but for the first two-thirds of the talk, I'm going to stick with the delta function analysis. Okay, the crucial thing here, the signal is defined to be the correlated signal. So 1 and 2 stands for Livingston and Hanford. And you just define the signal in such a correlated manner. And after some calculation, you can translate everything of the signal and noise calculation in terms of the plane wave calculation. So first of all, the signal is linearly proportional to the operation time. This is for the LIGO gravitational wave detector, the running time is about 2 years at the design sensitivity. And the other important ingredient is this gamma function. Gamma function is the so-called overlap function. It is the function to describe the correlation among different sides of my gravitational wave detector. I'm going to show you some properties of this later in the next slide. And this Q theta is the so-called optimal filter function. It is the function that will give us the maximize the signal noise ratio. And once you know the shape of your signal, you can easily build up this filter function. And at last, the noise of the gravitational wave detector is basically just Y noise at a fixed time. And the Y noise is, because it's Y noise, so the noise squared scale linearly with the total integration time. And the P1 and P2 here are just the one-sided string power spectrum. Okay. So now let's get into some details about this very interesting overlap function. And this overlap function is, I'm going to show you that our signal is giving us the overlap function, which is the best that you can imagine to have, and that is quite, something that is even better than Bertrand wave search. So the overlap function is defined to be the correlation of the first one and the second one, and then divided by the total noise. You just go, so for example, this detector is the one at Hanford, and this detector is the one at Livingston. And then you imagine that there is a Bertrand wave passing by. If there is a, for example, this is the stochastic Bertrand wave, is passing by, and then you look for the correlated signal for both of them, for each of them. And for the stochastic Bertrand wave, which is the totally random Bertrand wave background, then you can go ahead and calculate the overlap function. And the overlap function here is shown on this plot. The x-axis is the frequency, and the y-axis is the overlap function. And as you can see, that when the frequency of my Bertrand wave is very low, that means my wavelength of the Bertrand wave is very long. And that's where I start to benefit I start to saturate the overlap function. The overlap function here is about minus 0.9. The reason it's being minus is because for Livingston and Hanford, they are aligned up to 90 degrees. And it's not perfectly 1, it's because because of the curvature of the Earth, Livingston and Hanford, those two planes are not precisely parallel to each other. There's an intersection angle, which is about 27 degrees. So the maximum value of the overlap function that you can achieve is minus the absolute value. The absolute value is about 0.9. And then when you start to increase the frequency of your Bertrand wave signal, then you start to rapidly lose the overlap function. This is because for a stochastic Bertrand wave background, you start to lose the coherence right away after you pass one coherent region, and in that coherent region is precisely one wavelength. And that's where this point being 0 is precisely corresponding to the point where the wavelength between two Bertrand wave the wavelength of this 65 hertz Bertrand wave becomes the same as the separation between two detectors. And then you start to oscillate and gradually goes to 0. But for us, because our wavelength is much longer compared to the wavelength of the dark photon, compared to the wavelength of the gravitational wave. So even we are talking about the same frequency of the signal, our wavelength is much longer, and we always saturate the overlap function to its maximum value we can achieve. That is a very nice thing about the dark photon dark matter search versus the stochastic Bertrand wave search. And you can actually ask whether it is useful to include Virgo into this particular search. It is not that useful because Virgo is on the other side of the Earth, and because of the relative orientation, the difference between the orientation of the Bertrand wave detector, so the overlap function only saturates at around 0.25, and also Virgo doesn't achieve precisely as good sensitivity noise control as the LIGO Bertrand wave detector. So I think Virgo is good for confirmation of the signal, but it's not that fascinating to include Virgo to enhance the signal noise ratio. And one can also consider and calculate the overlap function for LISA, because LISA is a equal edge triangle. It's a different detector configuration. And also, as I mentioned, that for any pair, two pairs of the Bertrand wave, the laser interferometer detector, they have a common arm, and the noise is not totally disentangled from each other like LIGO. So in that case, you have to form a certain linear combination of those three pairs of the interferometer signals in order to make sure that the noise in those two linear combinations are totally independent to each other. And given this particular choice of the linear combination, you can calculate the overlap function by using A correlated with E. And in that case, it's giving us that for all the frequency that we are interested in, that the overlap function is about minus 0.3. Okay, so now we have a clear mind on how to calculate the signal noise ratio in terms of the strain of the Bertrand wave. And after that, it's just straightforward to interpret the sensitivity of the virtual wave string H0 in terms of the relative change of the arm length. And it's basically saying that if I have a monochromatic virtual wave with string H, that will generate exactly the same signal as the changing the relative arm length by amount of H, which is H defined the relative change of the arm length delta L over L. And once we have that, for a fixed value of signal noise ratio, we can get the maximum. We can get the sensitivity of the change of the arm length, and then that will be interpreted in terms of the dark photon dark matter Calvin constant at mass. Okay. So this is the result. The x-axis is the frequency, and it is one-to-one mapped to the dark photon mass. And as you can see here, that for the LIGO's most sensitive frequency regime is about 100 Hz. It's corresponding to the dark photon mass about 10 to the minus 13 to minus 12 eV. And for LISA, the best sensitivity on the frequency is about 0.01 Hz. That's corresponding to the dark photon mass about 10 to the minus 17 to 16 eV. And the y-axis here is the Calvin constant epsilon. And here I just take the epsilon squared. So the blue curve and the green curve, they are the current best constraints on the existence of dark photon. The green curve is the so-called the laser lunar ranging experiment, and the blue curve is the Edwards experiment, which is a torsion balance experiment, also operating in, I think, also in Washington. And laser lunar ranging is just shooting the laser from Earth to the moon, and then time on the reflected photon, so that you can precisely measure the distance between the Earth and the moon. And if there is dark photon exists in the nature, then there will be additional force between the moon and the Earth that will modify the orbit of the moon around the Earth. That's how we impose the constraints. So for those two existing constraints, there are no obvious signals being observed, so people put in the 2 sigma limits, and that is the best constraints that we have. And for the red curve, this the solid line is the 2 sigma exclusion line, assuming that LIGO is operating at the design sensitivity for 2 years, and we are doing the bump hunting experiment in the frequency space. And as you can see, that after 2 years operation at the design sensitivity, it carved into a large Hunter space compared to, especially at the region where Edwards experiments start to lose its power. And for the dashed curve, here is the 5 sigma discovery limit. This is because we are doing the bump hunting experiment, we have to include the lookout square effect, the 12 factors. So this 5 sigma has already included all the 12 factors in our research. So even for the U1B dark photon dark matter scenario, the LIGO can actually make a 5 sigma discovery in the unexplored Hunter space. And we even make the joke that if LIGO find dark matter in this way, we are going to suggest LIGO to change its name to LIGO to replace the gravitational wave by dark matter. And those brown curves are the LISA sensitivity curves. Again, the solid line is the 2 sigma, assuming no discovery after the 2-year operation, and the 5 sigma is the discovery line after you include the 12 factor. Okay, so and this is roughly the same plot, but applied for the U1B cell. There is a stronger limit coming from the Edwards experiment. If you change the dark photon from U1B gauge boson to U1B cell gauge boson, there is a factor of 5 difference. And also, at the meanwhile, you lose your sensitivity by a factor of 2 because of the smaller charge mass ratio. But the story still goes the same, that you can have the 2 sigma exclusion and the 5 sigma discovery limit for those 2 detectors. Okay, so now this is our plot for the O1, our preliminary result for the O1 data. So this is just the zoom-in version of my of my previous plot, assuming the dark photon is the U1B gauge boson. And this dashed line here is just the Edwards experiment 2 sigma limit. So this red curve, this is actually a curve, it's not a band. This is it is the 2 sigma exclusion limit for the LIGO 01 data. It's getting up and down all the time. It's because we are searching for thousands and thousands of those frequency bits, and you always get the fluctuation up and down all the time. That's why it looks like a band, but it's really a curve. Yes?
What are those resonances?
Oh, those things? Those things we have already identified. Those outliers are coming from either the violation mode, the violating mode, the string mode, vibration mode of the string that you attach to the mirror in order to suspend it from and isolate it from the Earth seismic noise. That's like those frequency bands over here, and there should also be a sharp signal showing up at around 60 hertz. That is actually where you start to see the AC frequency of the electricity in US. Yeah, and if you operate this in Virgo, then you see the peak at 50 hertz. Okay, so all those outliers we have already identified what they are coming from, and that's the region. That's the result that we have. And if you just average all of those rapidly oscillating red curves into the average value, you obtain this green curve. This is the average sensitivity, 2 sigma sensitivity, respect to the dark photon dark matter. And I'm sure you won't be able to see it, but this is where the dashed line is, and it's a little bit above the sensitivity that we can achieve using the 01 data. So within this teeny tiny mass window, we have already gone beyond the existing constraints, and that's the preliminary result that we are achieving using the 01 data. And one thing I want to just very quickly comment on is that this red curve, or this green curve, is based on a fixed frequency bin size choice. It is not the optimized bin size choice for the dark photon dark matter search, because as I mentioned previously, that the intrinsic width of the signal is about 10 to the minus 6 of the central value frequency. And so you should always make sure that the bin size is tuned, is chosen to be the optimized bin size. If you choose a larger bin size, then you include more noise in your analysis, but if you take a bin size to be too small, then you are losing the signal power. So this curve so far is just choosing the bin size to be about 10 to the minus 3 hertz, and this blue curve here, if you can see clearly, is the sensitivity that you should achieve if you optimize the choice of the bin size at each frequency. Okay, and again, this pink curve is just the 2 sigma sensitivity of the LIGO's design run for 2 years. Okay, so this is our preliminary result. And now let us go ahead for using the last 10 minutes to talk about some detailed signal power analysis. So if we want to, so as I mentioned previously, so far all the analysis is based on the bump counting search, and we really want to get into the detailed shape of the signal in order to further improve the sensitivity. But in order to get into the detailed shape of the power spectrum, you have to model the dark photon dark matter very precisely, or else work carefully. Because if you just treat it as just a bump, then you don't care about the detailed shape. But if you look into the shape of the bump, you have to be very careful on how the dark photon dark matter is evolving with time. So, for example, if we are talking about the signal at about 100 hertz, my direction, the propagation direction and polarization direction of the dark photon dark matter is going to change every hour. And for the whole 2-year operation, there are many hours, and we have to make sure that we model the gradual change of those of my dark photon dark matter background carefully. So the modeling is actually not difficult, because we know that everything is just a simple quantum mechanics. For you can imagine that I have the dark photon dark matter, and each of them is basically particles flying around. And all I need to do is to add up all those particles. Each of them is a plane wave, and I add up millions of those particles. And for each particles, I have my own random choice of the polarization for each particle, and I have my own random choice of the propagation direction at a random choice. And but the momentum here and the kinetic energy here, they are related. They are determined by the Maxwell distribution. So the magnitude of my velocity has to follow Maxwell distribution. And then at last, for each plane wave, I add in a random phase ranging from 0 to 2 pi. And basically now you just add in all of those particles, do a summation of all those plane waves. You can properly model your dark photon dark matter. This modeling of the dark photon dark matter will include all of the effects when you go beyond the coherent region. Okay, and this modeling will precisely tell us what the power spectrum should look like. And here, just to give you some intuition about how the coherent time and coherent length will behave, this is the result coming out of our simulation. So the x-axis here is the time in the unit of 10 to the 4 second, and the y-axis here is the magnitude of the gauge potential pointing to the x direction. This is fix the position and look at the time evolution. This is actually a very fast oscillating plot because we are choosing the frequency to be about 100 Hertz. And as you can see that when the time goes every about order 10 to the 4 seconds, you see the order 1 change of my dark photon dark matter profile. And this explains or give you the demonstration on what we mean by coherence time. If we are talking about a very short time scale, then everything can be approximately treated as a plane wave. But once we go beyond the time scale of the coherence time, then we start to see the order 1 change of my dark photon background profile. And the same thing on this plot is the spatial dependence of the AX field. And here is in the unit of 10 to the 10 meters, and the y-axis, the AX. And here, as you can see, that once I go beyond once the length scale is going beyond the coherent length, then I start to see the order 1 change of the profile. Okay. So with those simulation at hand, we can actually plug in those our simulated dark photon dark matter into the LIGO signal simulation package and calculate the signal noise ratio by ourselves. We don't have to rely on the data, and this serves as a very good cross-check on what we did theoretically and what we do here. And so the x here is the oscillation frequency. We choose the frequency to be about our signal frequency to be about 71 Hertz. And y-axis is the signal noise ratio. Those spikes are just a random noise coming from the detector. And as you can see, that by choosing the epsilon to be this much and choosing some particular choice of having the particular choice of the Fourier transform time and the observation time, we get the signal noise ratio within this small frequency regime. The signal noise ratio is about -8. It's why it's minus is still again because of the fact that the alignment between Livingston and Hanford there is a 90-degree roughly for the alignment. And this estimation for the signal noise ratio is very consistent with our theoretical prediction using those parameters. And one thing which is quite fascinating for us is that once you want to get into the details of the power of the signal shape, you have to be careful about the Earth rotation, because the Earth is rotating and it's rotating at the period of the day. And once you are talking about the coherence time, about hours, you have to include properly the Earth rotation effect. And if you just assume that my dark photon dark matter is a single plane wave, then it should be a delta function in the frequency space. But once you include the Earth rotation effect, it will split a single delta function into 5 delta peaks or 5 spikes in the frequency space, and the width for each is mainly determined by the window size of when I do the Fourier transform. But the key thing here is I'm splitting one delta function into 5 delta functions. And then this is just the result for one single particle, and we have to add up all those millions of those particles together, and this is the power spectrum that we obtain in our simulation. The blue curves, where the blue dots are coming from our numerical simulation by inserting our simulated dark photon dark matter into the LIGO simulation software. And you can see all those spiky features. I can explain those features later. But the key thing here is that the red curves is coming from our analytic calculation, given the dark photon dark matter simulation that we have. So the key message here is that even you see those pretty spiky features in the data, but we think we have a reasonably good understanding on what's going on, and we can actually predict the shape of the signal, those spiky features in our calculation. And why it's spiky, it is actually quite interesting in the sense that for each frequency beam, it is actually the result is is the result after you add up all those particles contribution in an interference way. And you have the real, when you do the Fourier transform, you take a real function, you convert a real function into a complex function. You have the real part and the imaginary part. And in order to properly calculate this thing, you have to include the interference. And that means you have to sum over all the real part and sum over all the imaginary part and then square. And then for each beam, the contribution is like a random walk. That's why there is such a jumpy and spiky feature in the frequency beam. If you do this without the interference effect, you just take every particle real part square plus the imaginary part square, then you get a smooth distribution. So this is the key thing about the interference showing up in the dark photon dark matter simulation. And that's a very, very cool feature that we think we can understand. Okay, so now, this template search is ongoing, and I don't have a prediction on the timeline, but hopefully within this year. And but now let me just conclude. So hopefully I convince you that the quantum wave detectors can be used for the purpose of the particle physics, and especially it can be used as a direct detection for this very special dark photon dark matter scenario. And the analysis is very straightforward. It is very similar to the so-called stochastic quantum wave search, and even better, the correlation for our signal is even better for all the frequencies that we are interested compared to the stochastic quantum wave search. And the sensitivity is very nice. O1 data has already beaten the existing experimental constraints, and we have the chance to have a 5 sigma discovery in the unexplored quantum space. Okay, thanks. Any more questions? Yes.
In your simulations,
Yes.
how did you decide how many plane waves to?
Very good. So that is actually determined by the energy density.
Right.
So a very quick back-of envelope estimation is that I can calculate the Broglie wavelength of my particle, and then let's calculate the cubic of the Broglie wavelength. That's the volume that I have, and then I can calculate how much energy I have within this volume, and take this energy divided by the mass of the dark photon particle. That's the number of dark photon particles that you should put in.
Okay, so these simulations were based on assuming a particular.
So that's actually a good catch. So this simulation is based on the add up of, let's say, 10 millions of those particles, either 1 million or 10 million, I can't remember. But the real number is much, much larger. But we actually checked our result for 10 million versus 1 million versus, say, 10,000. And the result, this spiky feature is remained the same. And the template search that we are going to do, we haven't done yet, is to look at the average of this shape. And then we can actually look at we can make a histogram of the difference from each beam corresponding to the average value. And then that should give us a feature predicted by the random walk. That is the template that we're going to build.
Okay.
And this feature is actually remains no matter how many particles you do the simulation.
Any other questions?
Just a comment, I suppose that this method can also be applied, extended to other models with the same fuzzy dark matter.
Yes.
All, we have other plans for.
Yes,
the
very,
future.
very good, very good. So this is actually one of the things that I haven't got the chance to do, but I think I should do that, which is actually for ADMX, which is a axion dark matter search. You have exactly this interference pattern that should worry about in the ADMX. So ADMX is actually you have to fine-tune the frequency of the resonance frequency when you operate the experiment, but they can actually operate one particular frequency for a long time and then get into the detailed shape of the dark matter. And for ADMX, if they get into the detailed shape, they should also see this kind of pattern. And that's the thing that how to calculate the power spectrum predicted in the ADMX is actually another thing that we have on our hand, and we haven't got the chance to figure out the detailed answer yet.
To say something earlier about the kinetic
Oh, yes.
mixing.
Yes. Good. So first of all, for the ones who are not familiar with the kinetic mixing, is the dark photon, which is quite different compared to the dark photon we are talking about right now. But it is a dark photon that is, roughly speaking, couples very weakly to the charged particles in our star sector. And of course, you can say that let's test the object at light or LISA. They are totally charge neutral. They shouldn't react at all to my dark photon dark matter if it couples to me through the kinetic mixing current. However, we just talked with those experimentalists, and they told me that they are trying their best to make their test object to be charge neutral. So even the best they are doing, for example, for LIGO's spectral wave detector, the mirror, they still have about 10 to the 6 of the electron charge on the mirror. They cannot remove. So that's actually giving us the hope that we can actually use those extra remaining charge to probe the kinetically mixed dark photon dark matter. And of course, here the price you have to pay is that you lower significantly the charge mass ratio. Because previously you got 10 to the 23 those charges, but now you have 10 to the 6 or 10 to the 8 of those charges. But meanwhile, you also gain in the sense that the kinetically mixed dark photon, their constraints are extremely weak in the low mass regime because of the so-called decoupling effect, that once you have the mass being very small, you can approximately redefine your photon and make the other kinetically mixed photon almost decoupled. So, for example, if we are talking about 10 to the minus 16 or 10 to the 14, minus 14, or even 10 to the minus 12 EV dark photon, the constraints is somewhere over there. That is almost like epsilon, like 10 to the minus 2 or 10 to the minus 3. But here we are talking about epsilon about 10.
So this epsilon can be interpreted as just the
Yes.
epsilon.
That's right.
Okay.
That's right. So there you just need to start with the remaining charge in the Gravitational wave
So
detector.
if it's 10 to the minus 6, then you just scale this thing by how many? What's the
Good.
power?
So this epsilon is about, let's say this epsilon is about 10 to the minus 24, and we change the charge mass ratio by 16 or 17 order of magnitude, because the total charge there is 10 to the 6, and total charge here is like Avogadro constant, which is 10 to the 23. So there is a 17 or 16 order of magnitude difference. So we have to compensate that loss by tuning up the epsilon. The epsilon here is about 10 to the minus 24. If you change it by 17 order of magnitude, that is about 10 to the minus 7. I think that's still there.
So you just want to persuade LIGO to charge up their mirrors.
I think that's a pretty hard suggestion for them, and that I'm pretty sure that will piss many people off.
Can they measure their charge very precisely? They know how much charge.
They have the order of magnitude estimation. on how many charges they have left on the mirror. If I remember correctly, that's like 10 to the 6 to 10 to the 8.
Well, if there are no more questions, let's thank Yue again.
Okay, thank you.